Okay, so today we're going to look at some actual skills that we will put to use in the next section when we are off to find the zeros of a polynomial. As of right now, we know how to find the zeros of a polynomial if it's factorable or if it's already been factored for us. So in order to get to the objective in 3.4 of finding the polynomials for finding the zeros for any polynomial, we need to go back and look at how do you divide polynomials. And there's a special case of division called synthetic division that we want to share with you. The results of both of these division techniques will lead us to the two theorems, the remainder theorem and the factor theorem. And these two theorems are going to help us out in the next section to give us a starting place to find all of the zeros for any given polynomial. So the first thing we want to look at, I wanted to take you back to using long division. Nowadays, most people have a calculator or they just estimate what the quotient is going to be. That's the answer to a division problem. And so I wanted to go back through the technique of doing this so that when we do get polynomials, you'll recognize the technique is exactly the same. It just is a little more confusing because you have variables to deal with. So let's take this first example here. It says 260 is to be divided by 15. And since this is a double-digit number, just a couple of things real quick to remind you of. The number 15 here is called the divisor. The number 260 is what we refer to as the dividend. And then when we get an answer, we'll have the quotient, and then sometimes you have what they call the remainder. So when we set this up for long division, the divisor sits outside of the long division mark, and 260, which is the dividend, goes underneath. And now it's going to sound kind of silly, but these are the things I want you to think about. When you start to divide 15 into 260, the first thing that you'll notice is that 15 will not divide into the 2 by itself. You need double digit since 15 is double digit. So we're going to look at how many times will 15 divide into 26. 15 divides into 26 one time. And with that 1, we're now going to multiply it by 15 to get the 15 that we'll place underneath the 26. And then in long division, or in any type of division, you're automatically doing subtraction. So we're going to subtract both 5 from the 6, which gives us a 1, and 1 from the 2, which also gives us a 1. Since we have another digit out here, we're going to drop down the 0. Now we're asking ourselves, how many times will 15 divide 110? And so we know that it has to be a single digit number. And so if you go through and do some multiplication, let's see, 8 times 15 is 120, so it's a little bit too big. So we're going to have to knock it back down to 7. And 7 times 15 then should be 105. And when we subtract that, 5 from 10 is 5, and then that's the only leftover we have. So 5 would be called the remainder. 17 is actually called the quotient. And there's a couple of different ways you can actually write your answer. The answer to this problem here could be 17 or 5. That's how we used to do it when we were little. And then we kind of got a little bit older, and we learned that this is actually also written as 17 and 5/15, which could also be then 17 and 1/3. And so this 17 and 5/15 was 17 is the quotient. So this was our quotient. 5 was the remainder, and 15 was the divisor. All right, let's try one that's a little bit bigger than that. We're going to have 18, and it's going to divide into 2,273. And we're going to do the same thing, of course. We're going to take 18, that's our divisor. We're going to take 2,273, which is the dividend. We're going to start our procedure all over again. Since 18 is a double-digit number, we know we need to start with double digits. So we're going to ask 18 divides 22 one time. 1 times 18 is 18. Built-in subtraction. We'll get ourselves a 4. We've got another term, so let's bring it down. 18 divides 47 twice. 2 times 18 is 36. We'll subtract. Both columns here, 6 from 7 is 1 and 3 from 4 is 1 also. We've got one more step to take because we have one more digit. 18 divides 113. We know this has to be a single digit number of times. If we go in there and we do some of the arithmetic, let's see, 5 times 18 is 90, and 6 times 18, well, that'll be 108. So 6 times 18, 108. Again, built-in subtraction. 8 from 13 is 5 remainder. So again, our answer here could be 126R5, or we could have written it as 126 and 5/18, which then would simplify to, oops, I take that back, it won't simplify, yay. Now what I want you to think about here is that when you talk about having a number, this is called a mixed number here because you have a whole number and a fraction. And this really is the same thing as 126 plus 5/18. This is what we know a mixed number really means. Just keep that in mind. All right, so when we move to polynomials and we want to do long division with them, there are 2 things that we want to make sure that we have before we get started with this division process. Number 1, make sure that the terms are always written in descending powers, okay? So the highest term first and the lowest term at the back. The other thing we want to make sure is that if for some reason you ever are missing a power of x, in that place, we're always going to plug in a 0. Now, in our first example, we won't need to worry about this one, but in the second one, I did get you ready for it, okay? So let's look at the first example. And this says we're going to divide 4x squared minus 23 plus 3. So this is playing the role of, this is playing the role of dividend. And this is my divisor. And you'll hear in the background, my bulldog has just come in from outside and is panting like crazy. Sorry about that. So if we now set up the problem, lay down, please. Thank you. 2x minus 5 divides 4x squared minus 23x plus 3. We're going to do this problem the same exact way. Actually, this one's a little bit easier. When we were up in that second example, and we were trying to figure out how many groups of 18 would go into 113, we had to kind of like run our multiplication for ourselves. So now what we're doing, let me kind of demonstrate. What we're saying is that I have this first value of 2x, just going to concentrate on the first digit or the first term. And I know I need to multiply it by something. And then I want it to equal to the first term of the dividend. So this is how I know how to get started. Take the first term of the divisor and try to match it to the first term of the dividend. In our case, we need to have a value here of 2x. And so 2x is going to start off the value of my quotient. This 2x, since x is the variable position, I'm going to put my 2x right here, since that's the x column. And now that I have this 2x there, I'm going to take my red 2x and I'm going to times them by both 2x and -5. We did the exact same thing, if you think about it, up here in the second example, when we said we needed 6 groups in order to divide in. So we had 6, and then we multiplied it by 18, and that's how we got the 108. So we're going to do the same thing. We're going to say 2x times 2x is 4x squared. We're going to have 2x times -5. And this is going to be now what we subtract from the first two terms. Now, when we go to subtract, and I had a lot of different color choices earlier in my notes. This one has a reserve of like 4 colors, but I'll try to demonstrate it here too. I think on the notes that are printed out for you, I did this in pink so that you would see what happens whenever we subtract a binomial. We've done this before. If you ever have to subtract a binomial, basically that just means that you're going to be changing both terms' signs. And when we change both terms' signs, that's taking the process of subtraction for us. So I'm going to come in here, and what I like to do is I like to kind of like put my new signs up here in circles so I recognize what's going on. I know in school a lot of times we would just mark through the existing signs, but I'm not too sure that you'll follow me if I do it that way. So now that I've gone through here and distributed my negative through the product there, now I'm going to add the columns together. Here's how you know if you're on the right track. 4x squared and a -4x squared is 0. That's how I know that I am doing this correctly. If the first terms that I was trying to make, if they actually subtract off each other and make 0, then that's what I want. From here on, you get what you get. So if I take a -23 and I add it to a 10, then I know that I'm going to end up with, from subtraction here, I'll end up with -13x's. Like before in the other 2 problems that we worked, if there's ever another term out there, you automatically drop it, and we start the procedure all over again. Okay, so now if I try to take my divisor, 2x again, and I know I have to times him by something, and I want to try to get him to be a -13x. Well, the best I can do here is to get it to be a 12x, because there's no way for me to actually get a 13x unless I use a fraction. So in this case here, I know that I can multiply this by a fraction number. And if I take 2 and divide that into 13, all right, that'll give me 6 1/2. So if I just wanted to put it this way, just for my purpose, -6 1/2, then that's going to give me now -13 if you times those 2 together with a variable of x. Now, the way I'm going to write this -6.5, I can't use a decimal up in there. They really don't want me to write a mixed number. So another way to write this, if I were to start it off as a mixed number, then you can change this into what we call the improper fraction. And what you'll do is you'll take the denominator 2, multiply it by 6, that's 12, add 1 to it, that's 13. So this is actually -13/2. So I'm going to then put up here my -13/2, and that's going to be my multiplier. So what we're showing here is that sometimes your divisors and sometimes your quotients will have fractions in them. It's not a big deal. We'll take care of it as we go through. All right, now what we want to do then is to multiply -13/2 times 2x. That will give me a -13x. That's what I wanted. And now on your calculator, if you'll multiply -13/2 times -5, and that'll end up being a positive, and we'll end up with 65/2. And now if we do our sign changes, this negative 13 now becomes positive. The positive 65 over 2 now becomes negative. And now we can add like terms together. Negative 13x and positive 13x is 0. 3 minus 65 over 2, if you'll put that on your calculator, then you'll find out that you'll end up with a negative, and it'll be 59 over 2. That is going to be your remainder. Okay. So one way we can write our answer then, of course, this is the quotient up here in the top portion. Let me change colors real quick to show you. This right here is definitely our quotient. A lot of times we'll put that this is Q of X because there's now an X variable in it. We can also come in here and say that negative 59 over 2 is what we call the remainder. And we'll actually put R of X just in case we ever end up with an X variable. Now, as I look at this problem, I think I did them a different way on the printed out notes. And so during class or during our meeting today, I'll show you what I did in that one. And this would actually be the correct answer here, though. Okay. Let's look at the second example. What you'll notice here, and you really have to pay attention to this, you'll notice that it is in descending order. Somehow we lost a parentheses in the typing of it. There we go. And we also notice that as you're counting down here, this is x to the third. What should have come next here should have been x squared, but there's not a term, so we're put in a 0. Then minus 23x plus 3. Your divisor, 2x minus 5. So your divisor is looking good here. All right, so when we set up this problem, then we're going to have a 2x minus 5. And that's going to divide into now 4x to the third plus 0x squared minus 23x's plus a 3. Let me block off this other problem real quick. All right. So now if we go back and once again, we try to do the same thing we did before. What we know that we have right now happens to be the leading term of the divisor is a 2x. What can I times that by to end up with a 4x to the third power this time? And the missing factor then would have to be a 2 with an x to the 2 power this time to get the third power total. So now you can see why we had that placeholder for the x squared term that was missing. When I go to place my dividend up above my dividend here, the quotient starts off as 2x squared. If I didn't have that column ready for him, I wouldn't have had a place to store him. We'll now go and do our multiplication. We'll have here 2x squared times 2x is 4x to the third. You always want to match whatever your first term is, because remember, subtraction is built in. And then 2x squared times a negative 5, well, that would be negative 10x squared. Again, we had to have that column in order to place this term. Now if we go to our built-in subtraction, from the last example, we saw that our signs basically change. So a positive 4x cubed now becomes negative, a negative 10x squared now becomes a positive, and we'll add our columns together. Let's see if we're on the right track. 4x to the third minus 4x to the third. Yep, they cancel each other out. Now when we go in there and we add the x squareds together, 0 plus 10 is 10. So we have a 10x squared. We're going to bring this next term down. start the procedure again. So again, starting off with a 2x, we know we'll have to times it by something to get 10x to the second. That missing factor then would have to be a 5 and also an x. This is a positive 5x, so we'll put plus 5x in its column. Do the multiplication. 2x times 5x is 10x squared. 5x times negative 5 is a negative 25x's. We'll go back to our setup of subtraction of a polynomial. So that means distribute the sign. So this now becomes negative. This now becomes the positive. See if you're on the right track. Did the first two terms cancel out? Yes, they did. 10 minus 10 is 10. Negative 23 and a positive 25 actually leaves us here with 2x. That's positive. We have one more term. Bring it down. That means you have one more division to do. So now the last division that we'll do, 2x we have times what will give you 2x. And so our missing factor here happens to be a 1. It's a positive 1 because that's a positive 2x that you're trying to build. And so now if I go in there and multiply the divisor by 1, then you'll end up with, get them out of the way, a sign change now. This is now a negative 2x's. This is now a positive 5. And so a positive 3 and a positive 5 will be positive 8 as our remainder. The 2x's did add up to be 0. And so now we have a remainder of 8. So if we were to write our final answer, one way we can do this, see if I can get this out of our way a little bit, will be the quotient is equal to 2x squared plus 5x plus 1. Your remainder is equal to 8. A little bit softer problem here, except for you had the missing term, but the numbers with the division turned out to be pretty nice. Let's see what this is going to help us do. I've got another example for you just in case. And in this example, you can see that we actually have a problem with the dividend. And the dividend is written backwards order as far as we're concerned for division. So one of the very first things that we're going to do is to come up here to the dividend and say, let's rewrite you as a 2x to the 4th, a minus 3x to the 3rd, a plus 5x squared, a minus 7x, and a plus 1. That's what's going to be divided then by x squared plus 3. Now what you'll notice here is that x squared plus 3 is actually missing a term. Now when it's the divisor, you have an option. I think it's a good option to use myself. I'm going to go ahead and load in the missing term, and that'll help me prepare for my division a little bit better. In the dividend, the powers ran 4, 3, 2, assumed 1, and 0. So all the powers are in descending order now. And now we can set up the problem. So now we have x squared plus 0x plus 3. We'll divide into 2x to the 4th minus 3x to the 3rd plus 5x squared minus 7x plus 1. Once again, we try to figure out what will the first term of the divisor need to be multiplied by to get the first term of your polynomial. And so we have here an x squared. We know we need to times it by something to get 2x to the 4th. Our choice then will be a 2, and then I need an x squared power to get to the 4th power. I'm going to go all the way over to the x squared column, since that's the term I'm using first, is an x squared term. Now think about it. We practiced this when we first did multiplication in polynomials. You now have a single term. Let me write them out here for you. You have a 2x squared, and you're about to multiply it by x squared plus 0x plus 3. So you have one term times 3 terms. One term times 3 terms is 3 terms. So you're about to fill in the first 3 columns for me. So 2x squared times x squared still is 2, but x to the 4th now. 2 times 0 is 0, and x times x squared is x cubed. So what I like to do here is I like to go ahead, and because 0 is neutral, you can use a plus sign or a minus sign. That's your choice. And then 2x squared times 3 is 6x squared. Once you do these enough, you'll kind of fall into the pattern of it. Now I need to go through there once again. Built-in subtraction for division. Everybody's sign will now change in my red polynomial. So now this becomes minus or negative. This is now minus or negative. This is now minus or negative. And now we're going to go in there and actually make sure that the first 2 terms canceled out when you added them. 2x to the 4th minus 2x to the 4th. Those are 0. We now have in the next columns negative 3 minus 0. Well, this is still negative 3 with the x cubed. We have 5 minus 6, which is a negative 1. I'll put the 1 in here like that so we can see it. And then I have another term to bring down. Traditionally, we only bring one term down at a time. There are times when you have to bring more than one, just FYI. All right, so let's start the procedure again now. I'm still dividing by an x squared term. I need to times him by something to make negative 3x to the 3rd. The missing factor here happens to be a negative 3. This time I only need an x. If you go to your quotient, you'll see that the 2x squared is there. So the next thing that you could have put anyway would have been an x term. And there's the negative 3x or minus 3x now. Let's go through the multiplication. Negative 3x times x squared is negative 3x cubed. Remember, you want these first terms to match because we will be changing the one in red to the opposite sign. Negative 3 times 0 is 0. I'm going to again put just a plus 0. That would have been the x squared column. And then negative 3 times 3 is negative 9 with an x. Let's go to place in now our subtraction. And remember, when we subtract a polynomial, that just means we change everybody's sign to their opposite. And so here in green, I've got our brand new signs. Negative 3 plus 3 is 0, so I know I'm on the right track. Negative 1 minus 0 is still just negative 1. I'm still going to carry that with that x squared term for us right now. Negative 7 plus 9 is actually going to be a positive 2x's. And we happen to have another term. We'll bring him down. All right, you're almost finished. When you bring your last term down, that means you're on your last multiplication to do for us. So we have an x squared in the divisor. What can we times him by to get negative 1x squared? And in our case, all we need is a factor of negative 1. I'll take that negative 1, put him up here in the quotient. I'll perform the multiplication. A negative 1 times x squared is negative 1x squared. A negative 1 times 0 is still 0x's. Negative 1 times 3 is a minus 3. come in and make our sign changes. When we multiply a polynomial by a negative, that's because of the built-in subtraction. This will become a positive number. That will become a negative, and this becomes a positive right there. So now let's go in there and make sure that the first terms did cancel. A negative 1x squared plus 1x squared. We have a 2 minus 0, which is still 2 for the x's. And we have a 1 plus 3, which is a 4. This is your remainder. So we say r of x is equal to 2x plus 4. And we say that our q of x, I'll put him back here in red for us, our q of x for this problem is 2x squared minus 3x minus 1. As you can see, long division is tedious, okay? And so anytime we can find a way around a long algorithm, which is a step-by-step procedure, we'll try to do. And so there is a special case of division. It's called synthetic division. It really is pretty fun once you learn how to do it. And right here it says that in synthetic division, nothing really changes as far as the dividend. The terms must be arranged in descending order. Again, put a 0 for anything that's a placeholder that's missing. And then the new thing for us here says that your divisor must always start off in the form as x minus c. Now what that literally means is that you and I want to make sure that our divisor here is linear. What that means is that if you ever want to divide a polynomial and you want to use this special form of division called synthetic division, your divisor can only have an x to the first power in it. If it has x squared, like our last example did, then it was not a candidate for synthetic division. So if you look at the first example here, you'll see that we have a great candidate here. Because back here in the divisor, right back here, this is your divisor, you'll see that you have of the form x minus c. It's to the first power that variable x is. And so we know we're in the right form. There is one thing that we have to prepare here for synthetic division. Synthetic division reminds me a lot of matrices. Don't panic. What I mean by that is when we went to build the matrices, they just had numbers in them and no variables anymore. And so that's why we make sure that everybody's term is there. We also make sure that all the terms are in descending order in the dividend. So the first thing I want to show you is that how's this divisor going to help us? This divisor, the first thing that we will do, we'll take x minus 3, we'll set them equal to 0, solve for x, and whatever number we get x equal to, this now is what we call the synthetic divisor. That's the synthetic divisor. If we'll go back to our dividend was missing a term. Right in here, he did not have a 0. He did not have an x squared term, so I'm going to have to place in a 0. When you set up synthetic division, they want it to look a little bit different than long division, just so you realize you're in a different type of problem. There's different forms of it. I was taught always to put my synthetic divisor, which in our case was a 3, in its own kind of like corner, so that everybody knew that that was the synthetic divisor. And then next to that, I could put in the values that I had for my dividend. And my dividend starts off as 4x cubed, so this is going to be the 4 that represents x cubed. The x squared column, well, he doesn't have a value in the polynomial, so I have to put a 0 as a placeholder. The next, this is kind of in our head what we're thinking about. This is the x cubed column. This is the x squared column. The next column that should be represented is the x, and so our x has a negative 28 coefficient. And then this last column here ends up being the constant column, and so our constant happens to be a negative 7. So all of the variables are out of the synthetic devising, because in this case, what we're doing is only looking at the coefficients and constants. The mathematics will always take 3 lines. Okay, 1 line to set up the problem like we've done here. We're going to skip a line, and then we're going to put a line right here to record what our answer is going to look like. Now, you may have to watch this a couple of times, but we'll do it also a couple of times in our work here just to kind of make sure that you have the right idea. Synthetic division, you need to have a starting place. And so the first or the highest, what we call the leading terms coefficient, we automatically bring that down. And so that 4 is going to start off our answer. Now, you'll see that we have 3 columns to still fill in. Every column that precedes a column will be its helper. For example, what I mean by that is, and I'll try to show you with some dashed lines here. If I take now to fill in this column right here, this place, then I'm going to take 3, I'm going to times it by 4, and I'm going to record the result right there. So in the green box then, I'm going to have what 3 times 4 is equal to. And 3 times 4 for us is going to give us the value of 12. Now, in synthetic division, we always add the columns together. Whereas in long division, we would subtract once we had everything in there. We actually go in and add. The subtraction feature has already been built in. When you and I went up here to find out what our divisor looked like, and we set him equal to 0, that's where the subtraction type of thing happens. Here, if we add our columns together, we get a 12. So what we're going to do now is we're going to look at the next column. And the next column has a place for us to put a number also. And so to get to that column's position, we now take 3. Let me erase these. See if I can get these little marks out of here for you without disturbing too much. Now what we'll do is we'll take 3 and we'll times it by the 12 that you got down here, and then that product will give you the next column's fill-in value. In our case, 3 times 12 happens to be 36. If you add negative 28 to 36, you do get 8. And again, we have 1 more column to fill in. And so we'll need to go in here and use the last calculated value in the bottom row here, and we'll take the number 3, and we'll take 3 and we'll times him by 8, and that product will go right there. And the product of 3 times 8 happens to be 24. Now we're going to add negative 7 and 24 together. That's our last column, so this is the last piece of work we need to do. And we do get the value of 17. Now, just like in long division, if you look at the example up above, once you and I brought down our last term here, let me get a highlighter so you can see where I'm at. When we brought this last term down, okay, And we figured out what would divide into that. The very last thing we wrote right here, ends up being the remainder. So it would make sense then if we were to go back and look at our problem. The last thing that we recorded in the synthetic division is the remainder. So this is your remainder. What's also kind of cool is that your quotient is down at the bottom of this problem, and the quotient is now written out to be q of x. This 4 is now 1 power less than what you started, so this will be 4x squared instead of 4x cubed, plus a 12. The 12 was in the x squared column, now he's just x. And then this is a positive 8, so plus 8. And it was in the x column, it's now going to be 1 less power, which is a constant. So here's our quotient, 4x squared plus 12x plus 8. And your remainder is 17. Now this is exactly what we were doing before in long division also. But you'll notice with the special case for synthetic division, it really doesn't take a lot of mathematics to get through. What it does is it just takes you at the very front of the problem to set this up correctly. Let's look at another example. In this example here, first of all, the first thing I always want to check for myself is, do I have a special case for synthetic division? And in this case, this is x to the first power plus 1. And so therefore I know that I'm going to be able to use synthetic division. In fact, I can go ahead and set up my synthetic division. The x plus 1, when it's equal to 0, x is going to equal to -1. So right here, I know that's going to be my synthetic divisor. Now the other thing that I just noticed was that I don't believe that our dividend is actually ready. Because if I look at the dividend here, that is not in descending order. And so if I put it in descending order before I get my work started, this would actually read 2x to the 4th, then plus 7x to the 3rd. There's missing term, isn't there? I don't see a squared term, so that would be 0x squared. I have minus 3x's plus a 5. Okay, let's see if all the terms are there. And like I said, I had to put in this missing term of x squared for us. So I think everything's in there correctly. The signs look good, so now we're ready to start. So out here in the division, the divisor here, we've already decided that's a -1. And we've looked at our dividend, and now in the order that it comes, it should be a 2, then a 7, then a 0, then a -3, and then a 5. We know we're going to add our columns up in the end. And in order for us to get started on this problem then, we're going to allow the value of 2, which is the leading coefficient of the polynomial, to come down and start us off. So now we have -1 times the 2. That will fill in the space in the second column here. And -1 times 2 happens to be a -2. Remember, in synthetic division, we always add. So 5 plus -2 actually ends up being 5. Now if we take -1 and multiply him by the 5 that you and I just got, then his value will load up the next column, and that'll be -5. When we add those two up then, we do get a -5. Once again, if we go in here and clean that guy out, we have another column for us to fill. And so you always use the number that's right before him down in the bottom of the problem here. So we're going to take our -1, we're going to multiply him by -5, and that will then become the value for the missing position in the column. This will actually end up being a 5. And -3 plus 5 is a 2. Last but not least then, we do have one more term up there. The column is missing right there. And so we'll take the -1, we will come in and multiply it by 2, and then that will become our value here. So -1 times 2 happens to be a -2. If we add these two numbers together, we do get a 3. And this just so happens to be the remainder. So again, if we go in there and we want to write out the answer back in polynomial form, we would say that the quotient, he'll start right here with the 2, and he's going to automatically lose a power. So the high power for us was x to the 4th. He's now down to x to the 3rd. So this will be 2x to the 3rd, a positive 5, x to the 2nd. We always just count down the powers now, minus 5 x's plus 2. This last number that I had blocked away from the quotient is the remainder, which is the number 3. In pre-cal, we do use long division for a couple of different reasons. We'll use a little bit of long division to show you what happens in the very last section of this chapter. Synthetic division is used when we can. Everybody likes to use synthetic division. All right, so here's pretty much our tools. So let's see what we can do with them. And one of the theorems that we'll be working with is called the remainder theorem. The remainder theorem has a very unique thing about it. And when we were working with polynomials before, we would always go in there and evaluate the polynomials at a value. So let's go into these two examples here where it says evaluate, so that we can go back over an old skill. And then I'll explain to you how the remainder theorem plays a role here for us. So for the first problem there, you'll notice it says right here, the example says f of x is equal to x to the 4th plus x cubed minus 6x squared minus 5x minus 15. They want us to evaluate when the function at 5. Evaluate the function at 5. And so basically what we know to do here is that this is the value of x inside of here. X is really 5. So what they're asking us to do is to go into the function here and plug in the number 5, just like we used to do. And we will then go to our calculator and find out what that value is going to be. Okay. And so if you'll put that in your calculator for me, let's see what we get. Okay, and I got a value of 560. Let me double check my work real quick. That is a minus 5 back here. It's hard to read. I'm sorry, minus 15 rather. There you go. And so I got the value of 560. We know how to do this, okay? This is just a plug-in. And so what this tells me is that when x is 5, then the function, or the y, as we know it, is 560. That's what that's telling me. Let's do the same thing for the second problem. This time they say just plug in -3 for us. And the reason why I chose to do another example of this is because when the insert, or the substitution here, is a negative number, it's super, super, super important that you use parentheses around your numbers that you plug in. So in our problem here, let me rewrite them over here. Okay. This would equal to a -3 is going to be raised to the 4th power. A -3 is raised to the 3rd power. Minus 6 times -3 squared. Minus 5 times -3. Minus 15. So now if we do this arithmetic on our calculator, we can find out what value we'll get. And I got 0. What this tells me is when x equals -3, y is 0 for this particular function. So now what we'll need to see is what in the heck does this actually mean? And well, we've got some really cool news here. When you find out that your function value is equal to 0, when you find out the function value is equal to 0, if you think about what this information is telling you, on the graph of f, you're going to have a point -3, 0. I just put my x and y as an ordered pair. This is an x-intercept. And what we're going to find out is that x-intercepts do provide what we call for polynomials zeros. Okay. All x-intercept will now be classified as 0 of the polynomial. So if we can find the function value, and the function value happens to be 0, then you've established the fact that -3, that's what we were dividing by, or substituting in rather. -3 is what we were substituted in. -3 will be one of our zeros. This is what this is telling me. In the first example, part A, notice that your function value turned out to be 560. What that tells me is that there's a point on this graph at 5, 560. That is way, way up high in the first quadrant. There's nothing unique about that value. It does not serve us a purpose at all. So let's look at how they'll actually ask the questions to us. In this example here, it says determine if c is a 0 of the polynomial. You'll notice here that the c value is already calculated, okay? And so if we take the c value, one thing we can do, according to the remainder theorem, we can actually take it in 2 different ways. We can say, well, let's go in here and find what is f of 2, because that's our c value. We're going to plug him in. And if we do that, we'll find out that this is 2 times 2 to the 4th minus 3 times 2 to the 2nd plus 5 times 2 minus 11. So if we'll calculate that, we can find out what the function's value is at 2. So let's see what we end up with. And I got 19. Well, what the remainder theorem says is that if you were to use synthetic division instead, you could have also have found the function's value to be 19. Now let's show you what that's going to look like. Let me block off this other problem that we did. Change colors for you. And so if you and I were looking at this through a synthetic division type problem, we would have said that 2 is our divisor. I know that whenever I look at my polynomial here, notice that he's missing a term. He's missing his x cubed term. So I'm going to have to put in there a 0 for the x cubed term. So 2 is going to divide 2, and then 0, and then -3, and 5, and -11. So this is a good way also to practice our synthetic division. If we drop down our first term, which is a 2, to fill in the first column, 2 times 2 is 4. Add the column together, you get 4. 2 times 4 is 8. If you add -3 to 8, you will get a 5. 2 times 5 is 10. If you add 10 and 5 together, you will get 15. 2 times 15 is 30. And remember, this back number here ends up being what they call the remainder of the synthetic division. That ends up being 19. So when you plug in a value for a function and you get an output, it's the same thing as if when we synthetically divide by that same number, we get the exact same remainder. So this also tells me here that there's a point xy where x is 2 and the y would have been 19. When I do the substitution, it also tells me that x is 2 and that the y is 19. This is not a 0. The reason why the number 2 is not a 0 is simply because you and I have a situation here where we have a remainder that is not 0. Okay, so determine if C is a 0 of the polynomial. Let me come in here so we can put a statement. 2 is not a 0. Write yourself a note. The reason we know that is because the remainder is not equal to 0. I'll put it here. The remainder was not equal to 0. The next 2 problems basically show that you can do this with all types of numbers, working as you're checking to see whether or not you have a 0 or not. You can definitely plug in the square root of 7 and see if you get 0 as a value, or you can synthetically divide by it. In your notes that I've written out, you'll see that. You can also take a complex number, 3 plus I. Now, if this complex number does give us a remainder of 0, or when you substitute it in, it gives you 0, it would be classified as a complex 0, okay, or what we would call an imaginary 0 if it does work, okay, if. And what you're not going to see then, imaginary zeros, they are not x-intercepts because you can't see them on the x-axis. However, they are going to be classified as zeros. So for time purposes, if you'll look to the written out examples for part B and part C, please see if you have any questions off of that, and I'll be more than happy to help you out with those too. I'm going to have to stop here. I do have another class that's about to start, so I will come back and finish this set of notes with the factor theorem.